Okie dokie, welcome back. This is the next video in the Dotpoint of projectile motion 1.3, the Dotpoint where we've been looking at applying some of the projectile motion questions. So in this video, we're going to look at a number of example questions and go through step by step using the methodology that we discussed in the previous video. As a quick reminder, previously we talked about two main types of problems you may see in a projectile motion question. First one being where the projectile starts and ends at the same height, and the second one being where the projectile starts at a different height to where it ends up at the end. In this video, we'll do an example of each type. We'll start with type 1 and move on to type 2. For the first type of question, just quickly, we know that we have a projectile. If we're starting and ending at the same height, some of the variables that you may come across that are either given in the question or asked for by the question include things like the time of flight, TF, the maximum height, HM, the range, and the initial velocity, angle, as well as the decomposed UY and UX component. The equations of motion that we previously discussed are listed here, and the problem-solving steps that we discussed included drawing a diagram of the situation, thinking about what info is given at the start, given and implied from the scenario itself. So this is one example of a scenario. What information is the question or problem asking for? How to link what you have with what you need via the equations of motion, which we have here. And then at the end, we take all that together and solve. So let's try our hand at an actual concrete example. So the ball is launched from the ground at 15 meters per second at an angle of 60 degrees to the horizontal. Assuming the ground is level, what is the time of flight? In other words, how long does it take the ball to land? What is the range of the ball? How far away does the ball land? And what is the maximum height? In other words, how far up from ground level does the ball reach? So, as we're looking at our problem-solving steps here, the first step is to draw a diagram of the situation. We have a ball at ground level, and it's launched at 15 meters per second at an angle of 60 degrees. Not the best diagram that I've drawn, but basically it's going to be reaching some point further away after its time of flight. Now, the first question is, what is the time of flight? How long does it take the ball to get from its starting position to its ending position? Right. So we've got some idea in terms of what we will need. As always, we can split these up into y and x components. So let's start thinking about what info we have given and implied. What info we have is u is equal to 15, theta is equal to 60 degrees, right? Even just using these two, we can say that ux is equal to 15 cos 60 and uy is equal to 15 sine 60 degrees. Remember, we get this from the fact that we have a right angle triangle. This is 15, this is 60 degrees, so therefore we have uy and ux, right? We've just used this triangle in order to derive these two equations. Calculating these would see that this is equal to approximately 7.5 meters per second, or exactly 7.5 meters per second, and this will be approximately 12.99 meters per second. If we look at the equations of motion, there are two that contain time, this one and this one. Because of the implied or the assumptions of the scenario, in other words, that the ball starts and ends at the same level, the same height, what that means is that the displacement in the y direction is actually equal to 0. In the y direction, it goes up and then back down to the same level. This can actually be used in these equations. Now, if we have this fact and we have ux and uy, right, what we need to look at is something that contains s and u, and of course, a. We know we're dealing with a projectile motion question. Ay is going to equal to negative 9.8 meters per second per second. So what can we do here? We can say that sy is equal to uyt plus a half ayt squared. Plugging in some values, we can see that we only have t left over, right? So This allows us to write 4.9t is equal to 12.99. In other words, what we've done here is divided each side by t, and then moved this over to the other side. TF, or the final flight time, is therefore equal to 12.99 divided by 4.9, which gives us 2.65 seconds. And that's our first answer. So it's important to note that we've looked at what info we had at the start, what info the question was asking for, TF, and we've linked it using this equation. We knew what uy was from the question. Ay was equal to negative 9.8, implied from the fact we're dealing with a projectile motion question. In other words, you have constant uniform acceleration in the downwards direction. And Sy was determined from the fact that we are dealing with a projectile motion question where the level the projectile starts and ends at are the same, right? The first type of question. This gave us this. This was implied from there. And really, we only had to use this from the question, right? So all variables except for the one we are looking for was covered in that equation right there. And then it's just a matter of solving, which we've now done. Rounding to the correct number of significant figures, which is 2 in this case, based on the number of significant figures in the question, gives us a final answer of 2.7 seconds. Okay, so let's move on to the next part of the question. What is the range of the ball? So quickly, just to redraw our diagram from before, we know that the projectile moves in the air, reaches some distance away, and lands. So the question now is, what is that range? We know from part 1 that the time of flight is 2.65 seconds. So that's part of the what info do you know at the start part, right? We've done the first part, we've redrawn the diagram. Now we're determining what information is given. So we know TF is equal to 2.65. Again, from before, we know that U is equal to 15 with 60 degrees to the horizontal being the direction. Based on that information, we also determined that UX was equal to 7.5 and UY was equal to approximately 12.99. Now, if we're talking about the range, what we're interested in is the horizontal component, right? Again, we know that we can split this up into X and Y components. But in this case, what we're interested in is the X position here and the X position there. What's the difference between those two? So effectively, we're going to be interested in what is SX, right? What's the range in the X direction? So now that we've got all the pieces of information at the start, what information is the question asking for, right? We've got that as well now. Link what you have with what you need via the equations of motion. So which equation here will give us that? Is it this one, or that one, right? Well, we know we need SX, so this is a good candidate. UX, we have TF, right? The total flight time. A, do we have A? Well, we know that in the X direction, AX is equal to 0, right? So in fact, we do have this as well. So it's really going to be this equation. This one's not going to work because we're not really interested in the final velocity. And this one could also work, but the problem here is that the final velocity and the initial velocity are going to be the same. UX is going to equal to VX. In the X direction, there is no acceleration. Therefore, this will make this equation unusable, right? So we're using that first one. SX is equal to UX TF. So effectively, you're just multiplying that initial X velocity by TF plus a half times 0 times T squared. Because this is 0, this all cancels out. Therefore, you're left with 7.5 times by 2.65. Therefore, the range is equal to 19.88. Rounding to the correct number of significant figures, our final answer is R is equal to 20 meters. And that's part 2. Okay, let's move on to part 3 of this question. So, quickly redrawing the diagram, we can see that we have our ball, 15 meters per second, 60 degrees. What we're interested in is the max height, right? So, what information do we have? Well, as before, we know that UX is equal to 7.5 meters per second. UI is equal to 12.99 meters per second. The total flight time is 2.56 seconds. And we also have some information that can be implied from this question, right? We talked about that before. So because the ball starts and ends at the same vertical displacement, right? We know the time taken to reach the maximum height is just going to equal to 1/2 of the total flight time. This was implied, right? Important part, implied from the scenario itself. So what you're going to get is 1.33 seconds. Again, we've redrawn the diagram. We know what information is given. With this step, we can always determine more, right? If we've missed something, we can go back and figure out maybe there's something we haven't considered, such as a y being equal to minus 9.8, right? We know we have gravity. Because we're dealing with something in the vertical direction, we're obviously going to be interested in everything in the vertical direction. So what is HM going to equal to? Well, in this case, it's going to be SY, right? So that's our big question mark. Is there something that contains all the information we need? Well, yes, the first equation is exactly what we're going to need. It contains Sy, our unknown, contains Uy times by Tm, right? We have both of those, and we know all the other information as well. So plugging everything in, and expressing our final answer to two significant figures, the maximum height is equal to 8.6 meters. Okay, now that we've finished a question where the projectile starts and ends at the same height, we also have the case, example 2, where we can have a projectile ending at a different height to where it began. Again, we have a number of variables you could be given or asked for, including the initial velocity, the time of flight, TF, the maximum height, how high up from the ground the projectile reaches, so it would reach here in this example, the x range, in other words, how far away from the x position it gets. Again, we'll be using the same equations of motion and the same problem solving steps. So let's get into an example. In this question, a cannonball is shot at a speed of 25 meters per second and 30 degrees to the horizontal from a 60-meter cliff. Questions are, how long is the cannonball in the air? What is the maximum height the cannonball reaches? And how far away from the cliff does the cannonball land? Basically, let's start off with a diagram, as we always do. Okay, so basically we've got a cliff, let's say it's 60 meters, right? It's labeled here. Projectile starts, launches at 25 meters per second, 30 degrees to the horizontal, and lands some distance away, right? Now, we've done the first point, we've got our diagram. What information do we have at the start, given and implied? So we know that U is equal to 25. Theta is equal to 30 degrees. This enables us to write up Ux and Uy. And we know that the ending position, the displacement with respect to y, is going to equal to negative 60. In this case, this is our 0 point, and the projectile ends 60 meters below that point, right? So, because this is not at the same height, one of the implied pieces of information here is that so the time taken to reach maximum height, Tm, is no longer cannot just be multiplied by 2 in order to get to Tf. Tf is no longer equal to 2 times Tm, because there is still some distance over which the ball needs to travel. We can call this distance, for example, or this time, for example, Tg. Anyway, the question is asking, what is total flight time? So what can we use? What do we have? Now, we know that the total displacement over the projectile's journey is negative 60, as we've written. We know that U is equal to Uy is equal to 12.5, and we know that Ay is equal to negative 9.8, as per usual in a projectile motion question. The one equation which incorporates all of these is this one right here. So, whereas before Sy was just equal to 0, simplifying this equation quite a bit, we now have to solve a quadratic equation, right? If we take these two terms over to the other side, we can use the quadratic equation in order to determine the answer. Just a reminder, it looks like this, negative b plus minus the square root of b squared minus 4ac divided by 2a. So if we plug everything in, this will give us something that looks like, we ignore the answer, that will give us a negative time, and that leaves us with 5.0 seconds. And that's the solution we're looking for. Okay, so let's move on to the second part of this question. What is the maximum height the cannonball reaches? Let's start off by drawing up the diagram again. And write down what we know about the initial question. What is the question asking for? Well, it is asking for the maximum height. In other words, when the ball reaches its peak in the parabola, what is the total height? Now, you have to notice that it's going to actually be split up into two parts, right? We know that the ball starts at one level, and we can split this off into two segments. So a segment where the ball reaches the same y position, and then the rest here, right? We can actually calculate this the way we've been doing for the previous scenario, right? We just have to find where Vy is equal to 0, and then add that distance onto the 60 meters that we know that this is, right? Okay, so let's try to do something like that. Here's the information we have. Here's the information we know about what happens at max height. And we know that hey, y is always equal to negative 9.8. We're talking about gravity here. So which of these equations can achieve that? Well, it's going to be the one right here. So Vy squared is equal to y squared plus 2ay sy, where our sy in this case is going to be that small segment right there. Let's plug some of these in. Putting this in our calculator gives us 7.972 meters. So all we need to do now to find HM is to add 60 meters to SY, and rounding to the right number of significant figures, we get our final answer, which is 68 meters. And that's the second part right there. And now for the final part of the question, part 3, how far away from the cliff does the cannonball land? So we've drawn our diagram, and our initial info is so as before, we've just included TF and HM, which were the answers to the previous two questions. So we have all this information, and we know that what we're interested in, last part, is how far away from the cliff does the cannonball land. Here's the cliff, here's where the cannonball lands, and we're saying how far away. So we're interested in the x direction, right? Now, this, otherwise known as the range, will give us the answer we're looking for. Because we're interested in the displacement in the x direction, Sx is basically what we're after. Right? So the range, we have a big question mark there. How are we going to find this out? Well, let's look at the equations that we have. So we want to find s in the x direction. We have u, the initial velocity in the x direction. We have the whole flight time t. And we also know that a in the x direction is equal to 0. There's no forces acting in that direction. So we can just write this out. Now it's just a matter of plugging it all in and putting it in the calculator, which gives us a final answer of 108.25. And if we round this up, we're just going to get 110 meters rounded to two significant figures. And that is our final answer. Well, that wraps this up. Thanks for the view, and hopefully this has shown you exactly how to apply some of these problem-solving strategies that we've talked about in the previous video. If you have any other questions, please let me know in the comments. Any other suggestions are also always very welcome. And of course, looking forward to hearing from you. Thanks for coming along, and I'll see you next time.